This video is going to be an introduction to Newton's law of universal gravitation and the Cavendish experiment, and I'm also going to go through several example problems related to the law of gravitation. But I want to first start with a quote from Albert Einstein. It just says, "Gravitation cannot be held responsible for people falling in love." You might think, like, why did he say that? People falling in love, gravity causes things to fall. Well, it turns out gravity is also an attractive force. We know this because when people stand in the earth, they have a weight. That attractive force is the gravitational force of attraction that the earth has on you or any object that has mass, right? So why are we attracted to the earth? It's because we have mass. And remember, Newton's third law says if something's getting pulled with a force, that means it must be pulling back with the same size force in the opposite direction. So the earth also feels a gravitational attractive force towards you when you feel an attractive force towards it. So gravity is always a mutual force of attraction between two objects that have mass. Because you have mass and the earth has mass, there's a mutual force of gravitational attraction. Let's go back to Einstein's quote. If we have two people, well, they both have mass. Therefore, wouldn't they feel a gravitational force of attraction between them? So if any two objects, including people that have mass, will mutually attract each other gravitationally, why don't we feel that force? Well, it's because that force is really, really small. And if that force exists, it takes a pretty sensitive experiment to show that that force actually exists between two masses. Einstein's quote doesn't suggest the gravitational attraction doesn't exist. It just suggests that it's not big enough to cause people to fall in love. So if we want to prove that this small gravitational attraction exists between two people or any two objects with mass, we need a pretty sensitive apparatus to detect that. There are a number of good YouTube videos that show and demonstrate this force of attraction between things like a lead brick and masses, or a bowling ball and some other masses, simple things that physics teachers set up, or a college apparatus setup. And I'm going to link those videos in the description below if you want to check those things out. All of these videos are trying to recreate the first historic experiment, which was able to measure the size of the gravitational attraction between two objects with mass, and that was known as the Cavendish Experiment, which we'll talk about later in this video. Probably the best video to watch, which shows a clear gravitational attraction between two masses, is one made by Mr. Lund Science, and I would encourage you to watch the whole video linked in the description below. His setup was very similar to the type of setup in the Cavendish experiment, which we'll talk about later. In his setup, he essentially hung 2 meter sticks in the middle by a string, and on either end of the meter stick, he just hung two masses. After a while, the meter stick didn't come perfectly to rest, but it essentially wasn't significantly rotating much about a certain position. And then he brought lead bricks close to both of those masses. And if there was a mutual attractive force between these two things, the left side would have been attracted up, the right side would have been attracted down, and would cause this thing to rotate in the clockwise direction from above, basically bringing these two things together. It's a very small force, so it's a very slow process. And so the part of the video that is clearest to see is when he speeds it up either 30 times or 50 times. Here's just a quick clip of when he sped it up 30 times. So when he brought the masses in, you can see that eventually over time, 30 times faster than normal, those masses on the end of the meter stick eventually came in contact with those lead bricks, showing that there was a very small attractive force that brought those two masses together. That video seems to show a fairly obvious attraction between those two masses, but the question is, how big is that attractive force? If you know the mass of the lead brick and you know the mass of the hanging masses and how far apart they're separated, let's say the middle of mass 1 to the middle of mass 2, which we'll call R, the distance from the center of one mass to the center of the other mass, how big is the attractive force of gravity that both of those masses feel towards one another? The first person to mathematically describe this attractive force was Isaac Newton, and in 1687, he published a mathematical derivation based on Kepler's laws of orbital motion, talking about how big this attractive force was. When Isaac Newton was alive in the 1600s, scientists already knew basic patterns about orbiting planets around the sun. They understood that orbits were ellipses. They understood that as a planet got closer to the sun, it sped up, and then it slowed down as it got farther away. They also understood mathematically what affected how long it took something to orbit a star, whether a planet around a star or a moon around a planet. And Isaac Newton used that with his understanding of gravity to come up with three mathematical relationships which talked about how to calculate the size of that gravitational force. So, without talking about how he derived it, we're just going to talk about what he understood. So, Isaac Newton understood that the gravitational attraction, let's say between the Earth and the moon, two things that have mass, number one was proportional to the mass of the planet. So, as the mass of a planet got bigger, the gravitational attraction it had on the moon would increase linearly. Through his mathematical derivations, he also found out that the gravitational force was also proportional to the mass of the orbiting object. So as the mass of the moon would get bigger, the gravitational attraction between the moon and the planet would also get bigger in a linear way. And lastly, Isaac Newton proposed that as the distance between the two objects, r, from the middle of one object to the middle of the object, as it got larger, they got farther away, the gravitational attraction between them actually got smaller. This type of trend shows that the gravitational force is proportional to 1 over the distance squared. So as the distance got bigger, let's say it got 2 times bigger, the gravitational force would get 4 times smaller. So these are not an equation to calculate the size of gravity. They're just how the force of gravity or the attraction between those two masses would change if we change either the two masses or we change the distances. These three individual proportionality statements could actually be joined into one proportionality statement that just says the size of the gravitational attraction between any two masses at any distance is proportional to the product of the two masses divided by the square of their distances. But again, this is just a proportionality, not an equation. So how do you turn a proportionality into an equation? Well, you need to multiply the proportionality, m1, m2 over r squared, times some proportionality constant. And this constant is actually not something Isaac Newton knew. He wasn't able to measure this experimentally. But think about this. If this equation is true, if we know the mass of both objects and we know the distance the center of the objects are separated, we can calculate what that constant is if you can measure the size of the attractive force between those two masses. And this is what Cavendish's experiment did back in the late 1700s. He was the first person to experimentally measure the size of the gravitational force between two objects with mass. So in the Cavendish experiment, which is very similar to the YouTube video that we saw, there's essentially something that was hung at rest by, in this case, a wire from the middle. And then Cavendish put about 1 kilogram masses on the end of that thing, so it was balanced. And then he brought in some really massive spheres, 158 kilograms, over 300 pounds. He basically put close to those 1 kilogram masses. And those two things, he was trying to figure out what's the size of the gravitational force of attraction between those two masses. Well, if you put one large mass here and another large mass here, this side of the apparatus would swing to the right, this one would swing to the left, and this whole thing would rotate in the clockwise direction. This wire would twist, and at some point it would stop twisting because the twisted wire would kind of push back. So it was balancing out the gravitational attraction between these two masses. And the angle through which this twisted allowed Henry Cavendish to calculate the size of the attraction between these two masses. So when Cavendish performed this experiment, he actually used the results just to calculate the density of the Earth compared to the density of water. And if you know the Earth's density and you know its size, you can figure out what its mass is. Well, scientists later on used something like the Cavendish experiment setup to determine this proportionality constant to finally make a complete equation that allows us to calculate the size of the gravitational attraction between any two objects with mass, and if we know the distance the two center of those masses are separated. So here is now the accepted proportionality constant for Newton's law of universal gravitation. We use a big G as the symbol to represent this constant, and the value is a really small number. It's 6.67 times 10 to the negative 11th, and the units of this constant are Newton meters squared divided by kilograms squared. You might think, well, why do we need all these units? Well, if we plug in kilograms for masses up here, we're going to have kilograms squared up top, and we're going to plug in a distance in meters down here. We're going to have meters squared down there. The units of this constant have to cancel out the kilograms squared up top. Look, there's one at the bottom. They have to cancel out the meters squared down below. This is up top. And all that's left over is just newtons because we want the size of the force of attraction between those two masses. And this equation is known as Newton's law of universal gravitation. In AP Physics 1, you've got this equation on your equation sheet. So now let's go through a couple examples using this equation. Let's go back to Einstein's quote. He said, "Gravitation cannot be held responsible for two people falling in love." So let's find out how big of a gravitational attraction exists between two people that have, let's say, a mass of 70 kilograms and a mass of 60 kilograms. And let's say the center of one person and the center of the other person are about 1 meter apart. Well, let's just plug in those values in this equation to see what the size of the gravitational attraction would be. So we plug in our universal gravitation constant of 6.67 times 10 to the negative 11th Newton meters squared over kilogram squared. We need to multiply that by mass 1 and mass 2. So that's the first person's mass is 70 kilograms, the second person's mass is 60 kilograms. And R stands for the separation between the center of masses, that's 1 meter. We have to square that. It's R squared in the denominator. And when you put this in your calculator correctly, you get about 2.8 times 10 to the negative 7th newtons. That's less than a third of a millionth of a newton. That's a really, really tiny force, right? That's why gravitation cannot be held responsible for two people falling in love, because the attractive force, it does exist. It's just very, very small. Well, what could make that gravitational force of attraction get bigger? Well, you could either increase the mass of either person or both, or you could change the separation distance. Let's say two people were standing, hip to hip. Their hips were touching. Well, the distance between the two people would not be 0. We'd have to plug in, remember, the distance from the center of one person to the center of another person. Let's just say that's about a third of a meter. So they're now 3 times closer, or 1/3 the original distance. Well, what would that new calculated force be? Well, let's crunch those numbers. So we've got our universal gravitation constant times the mass of person 1 times the mass of person 2. Though all of that is not changed. We're just now dividing by 0.33 meters squared, and that's going to lead to a larger force. It's about 25.7 times 10 to the negative 7th newtons. And if you compare this force is about 9 times larger, but still it's only about 0.6 millionths of a pound. So a very, very, very small force. And we could actually answer a question similar to this using just something called proportional reasoning, even if we didn't know the masses and the exact distances. So in my class, this is the first time we've talked about a proportional reasoning question. So here's what that would sound like. The question would be, how much does the gravitational force of attraction change if the distance is now 1/3 the original distance? Right? We already crunched numbers. We know that in this case, the force is a certain size. And when the radius got 3 times smaller, it was 1/3 the original radius, the force was 9 times bigger. But how could we answer that, like I said, using just proportional reasoning? So to start this proportional reasoning question, we're just going to write out the general equation and leave space in front of each of the variables which could change. The traction could change, the size of the masses could change, and the distance could change. And big G is a constant, so we don't put space in front of that. And let's say the original attraction, however big it is represented by this equation. And let's just say M1 represents the original mass of person number 1, M2 is the original mass of person 2, and whatever the original distance was, we'll just call that 1r. And that's going to give us, the gravitational attraction. So big G times M1 times M2 all over r squared will represent the original size of the gravitational attraction between these two people. So the question is, if we change one of these things, specifically the distance between the center of their masses, how does it affect the gravitational attraction? So to find out how it changes, we just rewrite our general equation again, and we change any coefficient in front of the symbol that changed. The first person's mass didn't change, so that's just going to be 1. The second person's mass didn't change, so we leave that as 1. But the distance from the center of mass 1 to the center of mass 2 is now 1/3 the original distance. So let's plug in 1/3 in front of r. Now, in order to find out how changing the radius affects the gravitational attraction, let's factor out all of the coefficients and leave all the symbols on the right. If we do that, we get 1 times 1 up top. That's just 1. On the bottom, we're factoring out 1/3 squared, right? If we have 1/3 r, we have to square everything inside of the parentheses. So that's 1/3 squared multiplied by r squared. So let's pull out the 1/3 squared in the denominator, and then we pull the symbols out here. So we get 1 divided by 1/3 squared times big G times M1 times M2 all over R squared. And remember, what did we say this represented? Right there, that represented the original gravitational force. And so let's simplify that. We now have, what's 1/3 squared in the denominator? That's 1/9. So we have 1 divided by 1/9 times the original gravitational force of attraction. And if we have 1 divided by 1/9, that simplifies to just 9. 9 times the original force. So the answer to the question would be the gravitational force of attraction is 9 times larger when the distance is 1/3 the original distance. Here's an example of how we could use Newton's law of universal gravitation to figure out the weight of somebody on the moon. So let's say we have a 70-kilogram person standing in the surface of the moon, and the question is, how heavy are they? What is their weight? Well, weight is the size of the gravitational attraction that the moon has on this astronaut. So we can use Newton's law of universal gravitation. It works for any two masses at any distance. So to find out the gravitational attraction that the moon has on the astronaut, let's kind of put Newton's law of universal gravitation in context. So the gravitational attraction is equal to the big G constant times the two masses of the objects attracting each other. There's the moon's mass attracting the person's mass and vice versa. The moon's mass in this case is 7.35 times 10 to the 22nd kilograms. The person's mass is given, that's 70 kilograms. And then we have to divide by R squared. Remember, R is the distance between the center of one object, that's the center of the moon, and the center of the second object, that's the center of the astronaut, right? So technically, that R would be the moon's radius plus half the height of the person. Let's think about this. The moon's radius, it's 1.74 times 10 to the 6th meters. That's 1,740,000 meters. If we just add half the height of a person, let's just for simplicity's sake, let's say it's 1 meter. We're adding 1 more meter. Either we're plugging in 1,740,000 or we're plugging in 1,740,001. That additional meter doesn't really change our answer much. And so when we solve these problems, if somebody is standing on the surface of a planet, we're going to ignore half of their height and just plug in the distance that they're separated by the radius of the planet, or in this case, the radius of the moon. So in the denominator, you're just going to plug in 1.74 times 10 to the 6th, the moon's radius, and square that. And when you crunch those numbers, you end up getting that the gravitational force of attraction on the person by the moon, and also on the moon by the person, is about 113.8 newtons. Compared to standing on the Earth, if you have a mass of 70 kilograms, you weigh approximately 700 newtons. The last example in this video is going to be a symbolic question. And if you're in AP Physics 1 or a college-level physics course, symbolic questions are something you have to understand and know how to solve. So here's one for you guys. So the question says, develop an expression for the gravitational field strength on a planet of radius r with mass m. So we don't know the actual mass. We're just going to call the mass of planet big M and the radius of that planet, spherical planet, big R. And we're trying to develop an expression for not the force of gravity, but the gravitational field strength on a planet. And we're going to only express our answer in terms of the planet's radius, the planet's mass, and any fundamental constants. Where have we heard of the gravitational field strength before? Think about the Earth. The Earth's gravitational field strength, and if you have the AP Physics 1 equation sheet or information sheet, it says the magnitude of the gravitational field strength at the Earth's surface, which we use a lowercase g to stand for, is equal to 9.8 newtons for each and every kilogram. It's the amount of force felt for every kilogram of mass at that location. So we want to try to figure out the amount of gravitational force felt for every kilogram of mass on this planet's surface. Well, if you know the gravitational field strength, let's say on the Earth, you can figure out the gravitational force on an object by taking the mass in kilograms times 9.8 newtons per kilogram or 10 newtons per kilogram. So if we just take this basic equation, Fg equals m times g, gravitational force equals mass times gravitational field strength, if we rearrange this for the gravitational field strength, or lowercase g, we get that the gravitational field strength at a location can be calculated, or an expression can be found if we can take the gravitational force on an object divided by the mass of that object. Well, we've got a planet here. We don't know the size of the gravitational force. We know the mass is lowercase m of the person. That's this right here. But we now have an equation, Newton's law of universal gravitation, to find an expression for the size of the attractive force on that person, right? That's just this. So big G times m1 times m2 divided by r squared, like this right here represents the size of the gravitational force on the person. So let's plug this in for the numerator and see what happens. So we've got gravitational field strength equals the gravitational force on the person divided by the mass of the person, not the mass of the planet. So that's lowercase m. And the gravitational attraction, like we said, is big G times m1 times m2 over the distance between the center of them squared, again, divided by the mass of the person. And let's now substitute in for the mass of the planet and the mass of the person, big M and little m, because those are the two masses attracting each other. That's what this thing tells us the size of the force of attraction between. So it's big G times the mass of the planet, big M, times the mass of the person, little m, divided by the distance between the middle of both masses squared. And like our last problem, we said that's basically just the radius of this planet. So that's big R, so we divide that by big R squared. And notice, what do we have? So now let's simplify our expression. The mass of the person actually cancels out because there's one in the denominator, there's one in the numerator, and so we get that the gravitational field strength at the surface of any planet is just equal to the universal gravitation constant big G times the planet's mass divided by the planet's radius squared. And this works for any planet or any spherical object of known mass and known radius. So what would this equation predict theoretically for the gravitational field strength at the Earth's surface? We've actually already measured in class what the gravitational field strength is experimentally. It's about 9.8 newtons per kilogram. So let's see if this equation gives us what we know to be true. So we'd have to know the radius of the Earth, we'd have to know the mass of the Earth, and that's what's given here. So the Earth's radius is about 6.38 times 10 to the 6 meters. The mass of the Earth is about 5.97 times 10 to the 24th kilograms. And so here's our big G constant, 6.67 times 10 to the negative 11th, Newton meters squared over kilogram squared. We have to multiply that by the Earth's mass, 5.97 times 10 to the 24th kilograms, and then divide by the Earth's radius squared. So it's 6.38 times 10 to the 6 meters squared. So this equation gives us that theoretically the gravitational field strength on the Earth's surface should be about 9.78 newtons per kilogram, which we know is true because we measured that experimentally in the lab. So hopefully this allows you to trust that this Newton's law of universal gravitation gives us answers that we know to be true. Now, before you're done with this video, I would strongly encourage you to practice typing in this equation just once to make sure you can get this answer. You just need to make sure that you're doing it properly because it's really easy to make mistakes and get wrong answers when you're plugging in scientific notation and you're squaring it in the denominator. So there's two ways to do it. Number one, you could type everything in just like you see it, like 6.67 times 10 to the negative 11th power times 5.97 times 10 to the 24th power. If you do it like this, if you type it in your calculator just like you see it on the paper, you have to use parentheses. If you don't use parentheses, you're going to get the wrong answer. There's actually a shortcut, though, that allows you to not enter parentheses. So on your calculator, most calculators have a button that's labeled E or double E. That button means times 10 to some power. So let's say we wanted to plug all this in to get our final answer. This is all you'd have to type in your calculator. You'd type in 6.67, hit the double E button, which means times 10 to some power. What power? To the negative 11th. This is the universal gravitation constant big G. And we don't have to put this in parentheses, and we just multiply this by the Earth's mass, 5.97 times 10 to the 24th power, or just type in double E 24, then say divided by the radius squared, which is 6.38 times 10 to the 6 meters. So just type in 6.38 double E, that means times 10 to, and then 6, the 6th power, and you square it. And again, if you do this, you do not have to use parentheses. You're going to get correct answers. So it really doesn't matter which way you do it. Just pick one and be consistent so you're not making mistakes.